Hey guys, this is our lecture over section 4.1. We're starting a brand new chapter. The first two sections of chapter 4 are about the laws of exponents. Before we get into the laws of exponents, we need to review what we know about exponents. And so the first thing I would say is let's discuss what we call the anatomy of an exponent. All right? And again, most of this we have discussed at one time or another back in the R chapter in section R5 or R6. Actually R5 when we did the exponents in the order of operations. If I have 2x to the third, this bottom portion here is known as the base. Obviously, this is the exponent. We did mention that exponents have other names like degree, power, and even sometimes we can call it the little number next to the big number. So the little number, obviously, exponent right there is its primary name, degree, power, little number next to big number, other names. This big number right here, does anybody know what that is called? That's called the coefficient. And it is always the big number next to the variable. And we're going to be using that word, and that's definitely a math term. And so we're gonna want to be familiar with the fact that the number is called the coefficient. Obviously, the letter or letters are called the variables. Okay. Sometimes you can have more than one variable in your base. You could have something like 2x squared y. Okay, that would all be a base right there. This right here and this right here are called the exponents. These numbers. And you say, what is that number right there? Well, if we don't have a number there, what is the power? It's to the power of 1. And so it's a silent one. It's not written, but we know it's there because anything to the 1 is itself. And so that is y to the 1. Those are the exponents. The rest is the base. Again, x and y are the variables. 2, the number, is the coefficient. Okay. Okay, and then we also learned what we call the 3 E's of exponents. And let's see if you guys can remember this. I'm going to just erase that right there. We're going to try to keep you nice and efficient today on these boards. The 3 E's of exponents, we have what we call exponential notation. Exponential notation. We have what we call expanded notation. And then we have what we call evaluated notation. And exponential notation, again, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. This is going to be 2, obviously 2 times 2, 2 times 2 times 2. And you remember this, with each one, we accordion it out. We are not saying 2 to the fifth equals 10. That's the number one error, okay, when it comes to exponents, is saying 2 to the fifth equals 10. Okay, no fumar, don't smoke that dope, right? Little numbers behave differently, as we stated, as they should, because they are different. This is 2 times itself, 5 times. When we multiply these out, you have 2 times 2 is 4, 4 times 2 is 8, times 2 is 16, times 2 is 32. So this is 32. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That's all for our review. We're going to pause for just a second.
Yep.
Okay, so Alex, can you see this whole board?
Yep.
Can you even see over here a little?
No, I can. Yeah.
Okay, all right, let's go ahead and let's just focus on this board. So we're going to discuss the laws of exponents. And we're going to make a chart, a big chart. There are 5 laws. The first one is called the 0 and 1 rule. So as I said, there are 5 laws in the laws of exponents, but we're going to cover 4 of them in section 4.1. So this lecture here today is over 4.1. We're going to do another one at 4.2, and we're going to hit the 5th law and talk about scientific notation. But section 4.1 is about the laws of exponents. We're going to make a little list on this left board over here, and this is going to be some of the things that make the laws of exponents unique. We'll talk about them. The first one is this idea, that little numbers behave differently, okay? And that's going to be one of our key factors here. Little numbers behave differently. Brother Rich better start drawing or writing more clearly for you. So this chart, we're going to have these big all things. So this is the name of the rule. Then we have what we call the hypothetical, okay? I don't know if you guys know what hypothetical means, but like a hypothetical situation, if you come into my office and you say, but Rich, I have a problem, okay? That's not a hypothetical situation. That's a specific problem to you. And then we talk about your problem and how we can solve it, what possible solutions there are, your feelings about it, my experience with it, anything we can do, draw on any, factors around us that we can solve your specific problem. But if you come to my office and you say, brothers, I have a friend that has a problem, that becomes a hypothetical situation where we're trying to solve something for anybody, right? It's a broader spectrum. We don't have as much specificity in what we're trying to solve there. Or, Brother Rich, what if a person had a problem like this? That's a hypothetical situation. So a hypothetical, approach to a law allows us to look at it in a broader way. We like specificity. That's when we get into examples. So we're going to do both. The hypothetical of the zero rule is that a to the 0 equals 1, and a to the 1 equals a. The hypothetical is going to take a little bit more root in the future laws. This is then when we go to our example, and in this instance we have 7 to the 0 equals 1 and 7 to the 1 equals 7. And then we're going to have this little section on the far right board. And indeed, are you able to see this side a little bit? Okay, so we're gonna call this the myth buster, okay? And we're gonna bust the myths here, because the big question here is, and this is kind of like why, okay? Why isn't x to the 0 equal to 0? Why isn't 7 to the 0 equal to 0? And this goes back to, little numbers behave differently than big numbers. Obviously, we know that x times 0 equals 0, 7 times 0 equals 0. These are true. Those are true statements. This is false, and this is false. But why does it equal 1? And we're going to discuss that, but not right now. Okay, we're going to come back to it. Let's come down here. Okay, so that is the first law of exponents. All right? The next rule is called the product rule. Okay, the product rule. And before we get into the product rule, we need to make sure that we have memorized these 4 words. So let's come on down here real quick. If we remember, we learned it a long time ago: sum, difference, product, and quotient. And each of these are respectively the answer to, this is an addition, a subtraction, multiplication, and division problem. Okay, we have to have these 4 words memorized. Let's come back here. So the product rule is going to have something to do with multiplying things. I'm going to go to the hypothetical here. A to the n times a to the m equals a to the n plus m. All right? So now you really start to see where the hypothetical takes root. There's no numerical values in that law right there. It's all variables. A's, n's, m's, and it's kind of ugly looking. Looks like calculus. Looks super complex. It's not as bad as you think. Let's do an example. If I have x to the second and I multiply that times x to the third, this equals x to the 2 plus 3, which therefore equals x to the 5th. Okay? And again, we need to get into our myth-busting portion here. And so we go to the y. All right? And so we're going to draw a little line here. Why doesn't x to the second times x to the third equal x to the 6th? Why? Why don't we get to multiply those two? I mean, big 2 times big 3 equals 6. And again, little numbers behave differently than big numbers, and so indeed this is different. And this one we are going to explain right now. We're going to tell you right now what we're dealing with and why we're dealing with it, okay? Before we do, draw your attention back to this board here where we have all of our list of things that identify what a law of exponent is. The laws of exponents are simply shortcuts, okay? When I was a little boy, I had to walk a long way to school, and there was a shortcut I could take. And rather than going to school being 30 minutes, which it took about 30 minutes to walk to school, This made it about a 10 to 12 minute journey. But I had to cut through somebody's backyard, and he was kind of a cantankerous dude, and he didn't like people, trespassing on his property, so it was always an adventure. The laws of exponents are indeed shortcuts, and I'm going to show you right now. Watch this. Would everybody agree with me that x to the second equals x times x? Okay, and x to the third equals x times x times x. So we got this and we got this. Now we were multiplying those two, so we're multiplying these. Let's count these up. X times x times x times x times x. People could say, well, that's 5 x's, but we call that x to the fifth. And so that's why this is x to the fifth, not x to the sixth. No Fumar, don't smoke that dope. So this is our myth buster. It doesn't equal what the big numbers would make. It's this, because this is just a shortcut. So sometimes I get students and they say, well, Brother Rich, I don't like using shortcuts. I don't want that cantankerous old man chasing me or yelling at me or swearing at me on my way to school. I'll just walk 30 minutes. Well, fetch you, man. I'm not walking 30 minutes to school. I'm going 12 minutes. I'm going in his backyard. And so let me tell you where you're going to say fetch you when it comes to math, okay? What if I have x to the 98th times x to the 101st, okay? You want to draw out 98 x's and 101 x's and do this? Or do you want to understand the concept is x to the 98 plus 101 would equal x to the 199th power, okay? That's a lot easier to do. We like that shortcut. So another thing that we're gonna talk about right here before we get into the next law is this little concept here on the far right board. You okay? Can you see me okay over here, Alex? I need you guys to understand the concept of x times x versus x plus x, okay? So when we multiply the bases, we change the exponents. And when we add or subtract the bases, we change the big number instead of the little number, which is known as the coefficient. Okay, so think about that. X times x is x squared, where x plus x is 2x. Notice the little number changed in multiplication, the big number changed when we were adding. That's a big deal. That's a big deal right there. And so, again, if we have x times x times x, is that 3x or is it x to the third? And you got to start demanding of yourself that you will not make this error. X plus x is 3x, but this is x to the third because they're all being multiplied. And this turns us to another idea. Let's come over here to our list of things. The laws of exponents, okay, in terms of the product and the quotient rules, we're about to learn the quotient rule, they apply only to things with the same base, all right? And so what we saw here in the product rule is that when we are multiplying, okay, we're going to add the exponents, but not anything. Only when we multiply things that have the same base, okay? For instance, look at this. If I have x to the second times x to the fifth, that'll equal x to the 2 plus 5, which equals x to the 7th. But if I have x to the second times y to the fifth, well, that's just going to be x to the second, y to the fifth. I can't combine those because their bases are different, okay? All right, let's go to our next rule. What's the opposite of multiplication, okay? Yeah, division. And so product means multiplication. What means division? Quotient. So we have, our next rule is called the quotient rule. I want you to think about this. In this one, we're going to take a to the n over a to the m. And we're going to say that that equals a to the n minus m. Kind of makes sense. The opposite of multiplication is division. In this one, we're adding for a shortcut. In this one, therefore, we'll do the opposite. We'll subtract for our shortcut. If I have x to the 15th over x to the 5th, this will equal x to the 15 minus 5, which equals x to the 10th. And of course, there's a y here. And people say, but, Brother Rich, why doesn't x to the 15th over x to the, put the cat out of the bag here, x to the 5th, why doesn't equal x to the 3rd? Because indeed, big numbers, 15 divided by 5 does equal 3. That's true in the big number realm, but this is not true. No Fumar, don't smoke that dope. And we can literally take x to the 15th over x to the 5th, and we can go the long way to school, and we can say x times 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 x. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 being multiplied, right? That's x to the 15th all over x times x times x times x times x. There's 5 of those there. Do you understand that x over x is 1? Absolutely. Cancel, 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 cancel. What's left on top? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they're not being added, so it's not 10x, they're being multiplied, so it's x to the 10th. And indeed, it does not equal x to the 3rd, okay? We can't divide them, no Fumar. Again, don't smoke that dope, because they're not big numbers. It equals what we have here, x to the 10th. Now, something interesting that happens here in the quotient rule, we're going to put a big or right here, or. A to the n over a to the m equals 1 over a to the m minus n. This frustrates people sometimes, and we're going to talk about it for just a moment. Before we do, okay, let's just write in here, when we divide, okay, we're going to subtract the exponents. Now, one of the things we once taught you is that the brain loves the path of least resistance. And so we like big minus small. We like, 7 minus 5 or 5 minus 7, right? 7 minus 5, absolutely, we like that. 2 is better than negative 2 in our world of, kind of thinking about things, all right? So another example here, if we were to take this one here, if I have x to the 2nd over x to the 5th, all right? I guess what I want to share with you, and again, please just bear with me. We'll explain all things in a moment. This is when n is greater than m. This is when m is greater than n. If we were to take this problem and apply what we've already done, we would say this is x to the 2 minus 5, which equals x to the negative 3. And that leads us to our next law. Now, if you're paying attention and you're following along with this, you may be like, that doesn't look like this. Like there isn't a 1 on top in this. We're going to come back to this here in a minute and explain that we can do this problem a different way if we wanted to. So our last law that we're going to learn in section 4.1 is what we call the negative exponent rule. Negative exponent rule. Okay? And the negative exponent rule simply says we can't have them, right? Okay, negative exponents are not considered simplified, and so we got to get rid of them. And so the hypothetical says that a to the negative n equals 1 over a to the positive n, and 1 over a to the negative m equals a to the positive m, okay? All right, examples. X to the negative 2 equals 1 over x squared. Interesting. We take this base and we bring it to its opposite place in the fraction, and this magically becomes positive. And if I have 1 over x to the negative 3, The same can work going the opposite way. This now equals x to the third. So now we put this in its opposite place in the fraction. It becomes positive. We're going to prove this. We're going to prove this with this problem right here in just a moment. Let's come over to the right board here, okay? You guys are cool. Let's do this. 15 over 5. Yeah, 15 over 5 equals 3 with big number. All right, let's go ahead and do this. So I want to show you something interesting about x to the second over x to the fifth in relation to this problem. X to the second over x to the fifth equals x times x over x times x times x times x times x. Agreed? So x to the second equals x times x to the fifth equals x times x times x times x. And again, we can simplify this and these can cancel out. I'm going to ask you what's left on top. Now sometimes students say nothing. There's no such thing as nothing in math. Nothing is not a number on a number line. If you've ever looked at a number line, there's not a value in math called nothing. There's 0. So then people say, well, there's 0. That's not 0. These are 1s, and 1 times 1 makes 1. So you have 1 left on top. What's left on bottom? It's not 3x. Don't go there. I've told you, if we're adding them, it's big number, 3x. We're multiplying, so it's x to the third. Okay? So the answer to this is 1 over x to the third. But I want you to look at what we just did right here. Right here, we took the quotient rule, and we said x to the second over x to the fifth. We think about this. X to the second over x to the fifth. Now, look at x to the second over x to the fifth equals 1 over x to the third. So these equal each other. But we also said that equals x to the 2 minus 5, according to the quotient rule, which equals x to the negative 3, which means that this and this are the same. So what's beautiful about all these laws of exponents, the shortcuts, is that we can prove these. These are called proofs. We use the laws to actually prove their own truths. So 1 over x to the third equals x to the negative 3 is how we take this shortcut right here, the negative exponent rule. So let's go ahead and write down here, what is it that we do with negative exponents, okay? We're going to put them in their opposite place in the fraction. And the exponent then becomes positive, all right? Very cool. Okay. Let's look at that for a second. Let's take just a moment and let's jump up to the top now. Why did x to the 0 equal 0? Now that we know all these rules, x to the third over x to the third. Anything divided by itself is what? It's 1. Y'all agree with me? This equals 1. But according to the quotient rule, this is also x to the 3 minus 3, right? Because when we have things with the same base, they're being divided, I can subtract their exponents. Well, 3 minus 3 is x to the 0. Therefore, 1 and x to the 0 are the same. So we just proved through the quotient rule, we proved the 0 rule, okay? All right, this is your chart. Now, coming back to this idea right here. Because we can't have negative exponents, and because we just showed you how we can take x to the second over x to the fifth makes 1 over x to the third, we can take this problem, and instead of doing it this way, making a negative exponent, we can use this kind of thing right here. Notice that 15 is bigger than 5, so we take 15 minus 5, and it stays on top because the top's the one with the bigger number, so that made x to the 10th. But in this instance, the bigger number's on the bottom, and so we could say, or right here, we could say x to the second over x to the fifth equals 1 over, notice how this is going to end up being 1 over right here when it gets to the answer, and that's a 5. It's going to be x to the big number, 5 minus 2. We bring this down, and that'll equal 1 over x to the third. And again, we know that x to the negative 3 equals 1 over x to the third. So that's kind of a faster way to do that problem if you so choose. Or you can make it a negative exponent and apply the negative exponent rule and just say that's 1 over x to the third. Now, if you've never seen the laws of exponents before, you might feel like you're drinking from a fire hose right now and your head's kind of spinning. So what we're going to do is we're going to give you one good shot, maybe just come back just for a moment, take the big picture of the whole board here. Is it okay to move the tripod? Just do that for just a second. We're gonna give you just one big shot of all the boards so you can see it all. And then we're gonna put it on pause and we're gonna put a bunch of problems on the board and we're gonna go through a number of problems together and see how rapid we can do this, okay? Once you have that, Alex, you can, that's cool. Good enough. Okay. Okay, guys, so in your homework tonight, you're gonna see that you're doing 4.1, you can leave it over there, 4.1, 1 through 101 odd. Actually, 4.1, 1 through 111 odd. And when you see that you have 111 problems, first thing of comfort, 111, you're doing the odds, that's half of them. You're like, well, thanks a lot, Brother Rich. We now have 56 problems instead of 111. That's good though. 56 is better than 111, but 56 is still a lot of problems. But up on the board here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 problems. And you're going to see that we can do these 13 problems in seconds. And there's very little work to be shown. One of the things that I want to inform you of is the laws of exponents aren't necessarily done in an order, like the order of operations. You can randomly apply them. The 0 and 1 rule, the product rule, quotient rule, and negative exponent rule. You can apply these randomly as they come at you until you've simplified something. Obviously, none of these have equal signs, so the laws of exponents are a simplified problem. We're just simplifying these expressions. I'm going to add one more problem up here. I want to put x to the second, x to the first, x to the 0 up here, okay? In fact, yeah, good enough. So let's look at this problem here. This one right here, these two are being multiplied. They have the same base, p. So this is the product rule, and I'm going to be writing down the names of the laws that we use for each of these. And the shortcut says we can take p to the 7 plus 12, and so this is p to the 19th. I'd encourage you at home to try these problems, and can you see all of them on this board right now? So if I were at home, I would pause, and I would try to do all these problems without me. Then I come back and see how we do them together. Again, this is the product rule, okay? And because they're being multiplied, they have the same base. We're going to say this is p to the 3 plus 5, which makes p to the 8. Okay? You can't multiply them. You can't say it's p to the 15th. All right? This is the quotient rule. Why? Because we're not multiplying. We are dividing right there. That's the fraction bar, which means division. So we're going to take p to the 7 minus 4. Okay? This is going to be p to the 3rd. I want to add another problem on this right here. What if we had p to the 4 over p to the 7? Okay, let's do this problem. What we're saying is now the bottom is bigger than the top. We could say this is p to the 4 minus 7, which equals p to the negative 3. And we can't have negative exponents, and we put them in their opposite place in the fractions. That becomes 1 over p to the 3rd. Or we could have, right from the get-go, said this is p to the 4th over p to the 7th equals 1 over p to the 7 minus 4, which equals 1 over p to the 3rd. Okay? That's another problem there. P to the 16 over 4, trying to tempt you to divide. 16 divided by 4 makes 4. That would be wrong. Again, this is the quotient rule. Notice here, in this problem right here, it is the quotient, but we ended up having to also apply the negative exponent rule too. That being this right here, this portion, getting us to this answer right here. Whereas if you just did it this way, it was just the alternate quotient rule, where you take the bigger minus the smaller from the bottom by putting 1 on the top. This one right here is going to be p to the 16 minus 4 is p to the 12th, and that's it. So you can see how these can go super, super fast. I'm actually going slow, okay? P to the 16 over p to the 16th, I mean, your brain's going to work super fast. Anything divided by itself is 1. You know, if you wanted to, you just say, hey, that's 1, fetchers. Or you can say that's p to the 16 minus 16, which is p to the 0, and anything to the 0 is 1. Either one of those, okay? All right, let's do these three right here, okay? So it doesn't matter. There's nothing written in between these, so we assume it's multiplication. You can put the dots in there if you want to, but it's going to be x to the 2 plus 5 plus 12. You get to add them all up. 2 plus 5 is 7 plus 12 is x to the 19th. Done. This is going to be x to the 2 plus negative 5 plus 10. Yeah, you can add the negative there. You say, well, do I have to get rid of it? Well, if it gets rid of itself, winner, winner, chicken dinner, right? So ultimately, 2 minus 5 is negative 3. Negative 3 plus 10 is 7. You can do x to the 7th. You can put all those in your calculator if you struggle with that. The answer is x to the 7th to this problem, and we're done. And that's good to go. This problem right here, x to the 2nd, x to the 1st, x to the 0, that's, x to the, 2 plus 1 plus 0, this is going to be x to the 3rd. Okay, simple as that. Some people are like, oh man, I got to change that to a 1. Yeah, and then if you did change that to a 1, let's just think about this. This is kind of the idea of you can apply the laws of exponents in any random order. You don't have to do it all at once. So if you said, hey, x to the 0 is 1, that would be times 1. Well, 1 times anything is just itself. That's x to the 2nd times x to the 1st. They're being multiplied. That's the quotient rule. I'm sorry, the product rule. X to the 2 plus 1 is x to the 3rd. All three of these right here are the product rule. Okay, every one of them. Because you get to multiply them all. All right? Let's come to this board. Okay? X to the negative 6. If we're going to simplify that, we're just going to put it 1 over x to the 6th. As simple as that. Just put it in its opposite place of the fraction, make it positive. Here we have 5x squared y to the negative 3rd. Well, check it out. There is a silent degree here. Okay, it is the 1. It's 5 to the 1 right there. Okay, that's terrible. We'll throw that away. Oh, I just hit somebody in the head. Did you hear that? They're getting stitches right now. All right, we'll use my good pen. Okay, that's 5 to the 1. That's better. Okay, that's 5 to the 1. So ultimately, and you're like, why do you care about that, Brother Rich? Well, I only care about it in the sense that I want to know it's positive. So I have 5x to the 2nd all over y to the 3rd. That's interesting. Okay, if you think about these are really all being multiplied. This right here has a negative exponent. It's going to go to its opposite place. But the other stuff stays up top. I want to take another problem here. What if I had negative 5x to the 2nd y to the negative 3rd? Okay, again, interesting. You'd have negative 5x to the 2nd over y to the 3rd would be the final answer to this problem right here. People say, well, doesn't that negative 5 come down and become positive? Well, we never had a problem with negative big numbers in the past. We don't have a problem with them now, okay? We have a problem with negative exponents. It's the negative exponents that got to change, not the negative big numbers. So that would just stay there. 5x to the negative 3rd. Let's try this one again. Try these at home before you get all these answers. Put your video on pause, try these, and see what you can come up with and see what happens. The 5 is going to stay on top of the fraction. X to the 3rd is going to, or x to the negative 3rd is going to come to the bottom and become positive, okay? 2x to the 0, this is the 0 rule. Ultimately, this is 2 times 1, which makes 2, right? X to the 1st over x to the negative 1. This is quotient rule. So I'm gonna basically, I'm just going to tell you all of these negative, exponent, okay? That is all of these 3 that we just did right here. This is the 0 rule, okay? That's the 0 rule. This one right here is the quotient rule. You could do it differently if you want to, but you're going to end up with x to the 1 minus negative 1. It's kind of cool, which makes x to the 1 plus 1, which makes x to the 2nd. You'll see that problem in the homework. It's a fun one. I don't know. I guess if you're weird like me and I'm a math teacher, I think that's kind of fun. Okay, this is kind of a combo here. Definitely product and negative exponent. All the same. We're going to end up with 5 x to the 2 plus negative 5 plus 3. Well, maybe it isn't going to end up being negative exponent because in the end here we're going to end up with 5 x to the 2 plus 3 is 5 minus 5 is x to the 0. Think about that. 2 and 3 makes 5. 5 minus 5 makes 0. X to the 0. So this ends up being not the negative exponent rule, but the 0 rule. And if x to the 0 is 1, 5 times 1 is 5. The answer to that is 5. Another cool one, all right? Lots of examples there. Good luck with that homework. Have fun. Fly through it.